afternoon. I'm Ellie Walmark, and welcome to the ICM Research in Focus podcast series. So today I have with me Wray and Bill McGough to talk about their differing approaches to research into kidney cancer using AI. Rebecca is an MRes PhD student investigating the response and resistance to therapy in patients with kidney cancer. She uses AI to find tumour features at multiple scales. For his PhD, Bill is developing AI models that will sift through mounds of imaging data produced during the Yorkshire Kidney Screening Trial, flagging images that show masses in the kidneys. So to start with, please could you both briefly outline your current research focuses in a little bit more detail, please? Rebecca, do you want to go first?
Sure. So I'm really interested in understanding how we can prescribe kidney cancer treatments with better accuracy. In kidney cancer, this is really important because two patients with exactly the same type of disease can be treated with exactly the same drug and respond completely differently. And I want to understand why that is and how we can predict that before we give them the therapy.
That sounds like an excellent idea. And Bill, tell us about what you do.
Yeah, hi. So my work is in the screening space. So in the UK, we currently screen for 4 or 5 cancers nationally. And this is a missed opportunity. But the fact is, so screening in general reduces cancer mortality because when you find the disease earlier, it's more treatable. It's also less costly to treat. So it's better for everyone if you can find cancers earlier. People survive longer and it costs less to treat. That being said, it's very expensive. And so what I'm looking at in my PhD is, can we automate the process of screening using AI and basically unlock screening for kidney cancer that hasn't yet been available traditionally within our hospitals and within our GP clinics?
Great, thank you. And Rebecca, so I said in your introduction that you study cancer tumours at multiple scales. So what does that actually mean?
Yeah, great question. So when I say multiple scales, what I mean is at different magnifications. So I start with clinical data from the whole patient. So I take blood samples and I analyze the blood for different proteins, which can show us, for example, a whole body immune response, which can maybe point towards something which may help us to understand a patient's response to treatment. But then I also have MRI scans, which show me the tumor in 3 dimensions, and they show me the tumor's position within the kidney. I then have slices of the tumor tissue. So after it's been removed from the patient, we take a slice of it, look at it under the microscope, take a photograph of it at really high resolution. So it means that I can see individual cells within the tumor. And then at the smallest scale, I have data from DNA and RNA, these really small molecules, which help me to understand the tumor a bit better.
And why is that important when you're trying to understand why patients would respond differently to treatment?
So a lot of the research in this field at the moment only looks at one of these scales. And my hypothesis is that we can use all of these data from lots of different magnifications or different scales to gain additional insights into how the patient will respond to different types of therapy. And then we'll be able to make more accurate prescriptions, taking all of these types of data into account.
That sounds, like just exactly what integrated cancer medicine is all about. And then how then would you employ the AI in your research? So you've got all these different data streams. How do you employ AI to help you?
Yep. So I use AI in multiple different steps, really. I use it to extract data from the MRI scans. I use it to extract data from the tumor tissue. I'm hoping to also use it to extract information from the molecular data. So that's the DNA or the RNA data. But then I also actually use AI to integrate all of this information together and to find which are the most important features from each of these scales, which may help me in answering my question.
And when you say you're hoping to, is that something that you're developing currently, or is that a new technique? Yeah.
We actually just published some work which was looking at using AI to find the most important features for prescribing kidney cancer patients with a certain type of drug. And I'm now extending that work into looking at different types of drug in a slightly different clinical scenario of kidney cancer, but still very much related to this previous work. And the hope is, we're working very closely with clinicians. So the hope is that eventually this model will be able to be deployed in the clinic and used regularly by oncologists who are working in this space.
That's great. So Bill, tell us about your use of AI and your work within the screening programme. How do you use AI in that setting?
Sure. As I mentioned earlier, screening is very expensive. It's for this reason, among others, that screening for kidney cancer is not possible. So there are perhaps methods that we could already be screening for kidney cancer that would work, but we couldn't justify the cost. And you might think, well, why not? Saving lives is worth it. But when we look across the whole NHS, we have to justify costs. Why spend 500 million on a kidney cancer screening program when we could spend 500 million building a new hospital, or providing new beds, or hiring new staff, or pay rises, or whatever it might be across the NHS? And so you've really got to justify your clinical interventions with a costs analysis. And so for many interventions that we'd like to do, the decision to not go forward is due to cost. And this is the case in kidney cancer. So, for example, what we could do, hypothetically, is give everyone a CT scan when they reach 55, just for the sole purpose of kidney cancer, to see if there is a cancer present or not. I think there's roughly 20 million people who would be eligible for that in the UK. It's in that order of magnitude. And a CT scan is about £120. And so that 500 million figure is not, that's about the right order of magnitude. That's for a one-off screening program, let alone yearly. And so you start to get a sense of how these costs scale up. What we're looking at is, if you attach kidney cancer screening onto existing screening trials and use AI to capture the kidney analysis aspect, can we reduce the cost enough to make it cost effective? Can we plug kidney cancer screening as a piggyback onto another screening program using AI to essentially get another free program? And so what my AI looks at, the kind of technologies we're developing, is automatic pattern recognition within images. So lung cancer screening already exists in the UK. This is a CT form of screening. There are roughly 1 million scans done a year, and it's going to scale up to about 2 to 3 million by 2030. And what we're looking at is, well, the kidneys are quite close to the lung. They're just 10 centimeters down. And so if we extend that scan by 10 centimeters and add AI on top, can we capture the kidneys for free? We're developing the technology that will automatically analyze the kidneys.
That sounds like such a sensible idea, because if you're already screening for one thing, why not just screen for another? Very clever. So what stage of AI model development are you both currently at? So are you developing your own models, or are you using somebody else's models? Where are you both at in the process of development? Bill, do you want to tell us first?
Sure, yeah. And I think when answering this, it's important to recognize that for some approaches, models will be closer to the clinic inherently. So, for example, the screening trials are already being performed within clinics for kidney cancer. And so when I develop a model, it will be tested within a clinical trial setting. That puts it quite close to the clinic. So in terms of stage of model development, we're looking at something relatively far along in this clinically, just because of that's where screening is. It's been assessed now. There's already been clinical trials in this, and we're on to the next phases of clinical trials. So clinically, we're quite far along. Whereas perhaps in other sectors or other parts of the clinical pathway, like, for example, AI for analysing and pulling together data from different scales, perhaps that's, well, Greg can talk about that. But essentially in screening, we're looking at something that can be hopefully plugged in the next 5 to 10 years. These models that we're developing, yeah, we've trained from scratch, actually. And so what we've done is we've taken data from the hospital, from patients who have, you know, we're very grateful they've consented to having their data be used for research purposes. And so for every patient that does that, our model improves its learning. And so we're able to look at patients who are young and old and male and female and all different body types. And we can source that data right from the hospital. And I guess over the course of 3 years throughout my PhD, we've been perfecting those models. And within the next year, it's going to be prospectively tested within another clinical trial. And so we're quite mature. This is going to be tested alongside radiologists within the next couple of years, which is quite exciting.
Yeah, that's really exciting. So when you say prospectively tested, that is like real-time patient, real-world, real-time patient data that you're going to be using?
Yeah, so that real-time is a particular sticking point, whether we can get it in front of doctors before they assess. That's a point of negotiation right now. But one thing that can be done is, so for example, in a screening trial, often results will have to be assessed by 2 doctors rather than just one. And what we might be able to do is substitute one of those doctors for our AI and see how that pipeline performs. It's unlikely that we'll be able to completely triage using AI in this screening trial. And so it's likely that what will happen is a doctor will review an image and alongside an AI will also review. And within a week, if there's a disagreement, our AI will suggest, hey, look at this image again. There might be a cancer that you missed.
So it's like an automatic validation, really, isn't it?
Exactly.
Yeah. And then, Rebecca, tell us about your work. So my question was, where are you at in the state of development with the AI?
Yeah, so mine is slightly different to Bill's in that I think, as I said before, nobody's really done this kind of integration at multiple scales, multiple magnifications, whatever you want to call it, before. So I'm a bit earlier on in that development. And really, I'm interested in using, the model both for deployment in the clinic, but also for actually understanding the cancer better. And so as my project moves forward, we'll really start to understand how we can use AI better for kind of both prongs of that. Is it possible that we can develop a tool that clinicians can use in their appointments with patients in real time, but also can we identify what are the features of these cancers which are most useful for doing that treatment decision, clinical decision making. So I'm a bit earlier on in that process, I would say.
That makes sense. So partly kind of filtering the noise to get to the really salient points of what is going to impact treatment decisions.
Yeah, just because so much is unknown in this space. It's been a question that's remained unanswered for decades now in kidney cancer. So yeah.
And do you think, either of you, that your AI use would be used outside of kidney cancer? Is it something that you could transfer to other cancers? I mean, with a bit of tweaking, or even just as it is? Is that something that you could consider?
Yes, definitely. I think it would require a lot of extra work, obviously. Certainly the whole patient data that I'm looking at would be similar between different cancer patients, different types of cancer, different diseases. But when you're looking at a tissue level, some of the arrangements and structures of these cancers can look really different depending on the organ where the cancer is. So yeah, definitely the hope would be that we could use this in a kind of all types of cancer sort of decision making, but it would require some extra work and some extra data.
And Bill?
Yeah, so we have this idea as AI being like a robot, and we give it data and it learns what to do with it, and it can make sensible generalizations. And I think a more appropriate model is like a data-centric model. So we have methods of making of sorting data. That's what AI is in a way. It's something that sorts data, and it's so dependent upon the specific task that you want it to do. Now, good models generalize well. And so ChatGPT will write a poem and it will organize your holiday and it will help you write a document. Fine. That generalizes well. But really, it's because it's been trained on all of those tasks. What we're looking at is something quite specific in its data use. And so for kidney cancer, what we're looking at is ways of sorting between those who likely do and do not have cancer. That's my screening work. The same methods could definitely be used across all different domains. And in fact, they have. So lots of people have looked at this with lung cancer and pancreatic cancer and also breast cancer. But the appropriate way to think about this is something that extracts insights from the data and helps you sort the data that you have. And so it would be inappropriate to take our work and apply it directly to kidney cancer. However, if you were able to get your hands on data from different sources, or from all of these sources at the same time, you would probably be able to not only sort through each of these individual cancers or whatever you're trying to do in your screening program better individually. So you'd be able to do them each individually better. I guess at a high level, what the important takeaway is, yes, you could generalize AI to other domains, but it really depends on what you're training it to do in the first place.
Yeah, thank you. That's a great clarification. So you're using a lot of data when you're building your models and using your models, training them. How do you ensure safety and how do you mitigate bias? Who wants to take that one first?
I'm happy to try and give that one a go. Yeah, look, so bias is desirable. Bias is actually desirable. For example, when you're looking at a CT scan, it's important you have some assumptions and biases going into it as to what a normal human looks like. That's extremely important. It's also important to know that a vein typically looks like this, and the renal cortex typically looks like that. It's important because that's how you identify anomalies. It's how you actually identify cancers, is a stray away from the internal bias that you've helped develop. The useful bias that you've developed helps you identify anomalies. How you ensure you don't have unuseful biases is by factoring them in. And it's only the conscious effort of, say, collecting data from different ethnicities and genders, large and small body types, that you can factor those into your data. But I'd just like to kind of, push back a little bit and just kind of highlight how useful biases are in sorting data. And it's not like a sexy topic by any means, and it's not something people think of as a positive. But it's what makes AI so efficient and so useful, is that we can identify these kind of regular patterns that do appear in images, and that forms the AI's bias in a useful way. Safety is, for us in the screening space, it's all about clinical trials. And so, yes, you've developed a model and you can quote performance and you can talk to clinicians about how it works, and perhaps it can report back to you where it thinks a cancer is and how large it is. And so there's feedback and there's some understandable interpretability aspects going on with your model. But the only way you're going to ensure safety is the same pathway you ensure safety with drugs and hardware, like medical equipment, is a clinical trial. You need to test it first across multiple domains with doctors in a safe environment to make sure it's safe before it can be rolled out.
I love your answer about bias. No one has ever put it in that perspective before. So that is really insightful and really interesting. Thank you. Rebecca, did you want to make a comment about that as well?
Yeah, I don't have much to add other than the kind of models that I'm working with, which have been developed really in the last year, 2 years, I'd say maybe 5, are ones that are, you basically have what's called a foundation model, which is built from like millions and millions of images. And because I basically use that foundation model to understand my images better. So I'm taking a really broad foundation and finding the features of those images and understanding how the images that I have from the clinical trial that I'm working on fit into a much broader landscape, which ideally kind of encompasses a real range of kind of diversity and backgrounds, which is a really useful technique in AI, which a lot of us are employing now.
Thank you. We've talked a bit about them being used in a clinical setting. So Bill, yours is we're almost there, or you're on the cusp, or it is being used in a clinical setting. And Rebecca's, yours is a bit further away, just being used in the research setting. Is that right? Have I got that right? Those distinctions right?
Not quite yet. I mean, so it's in the clinical research setting, the screening work. So we're not near it being used in the NHS. We're not near the replacement of radiologists, but we are seeing how we might go about in the future. And so we're at the stage of putting it in the clinic in a research trial environment. It's a little further along, but it's 5 or 10 years away at least.
Okay, thank you. And how do you think it will affect a patient's treatment journey? Will it make it quicker? Will it, what impact is it going to have on patients?
Yeah, there are ways that both of our like different kind of workflows will contribute to this. I mean, obviously Bill's work really is centered on finding cancers earlier. And we know that particularly in kidney cancer, when you identify a tumour that's stage 1 or stage 2, you have a much higher likelihood of a longer survival, a much higher likelihood of cure than when you catch a cancer that's stage 3 or 4. And so we anticipate that using AI for that task will improve survival rates from this disease. We also really, I mean, AI is very quick and it's much cheaper. And so really in our ideal world, I suppose, from our perspective as researchers in this space, is that we expect that AI will introduce shorter waiting times, that patients will have shorter waits in between having symptoms or going for screening or whatever it is, and actually, being treated or understanding what the disease is that they've got.
Do you have anything to add, Bill?
Yeah, just something small. I think that's a perfect summary. I guess just as a kind of tangential thought, just to have a slightly different perspective as well, is It's going to be the difference between introducing new pathways and not. So the question is, how will it affect the patient's treatment journey? It might be that in the future, a patient, so currently more than half of kidney cancers right now are found by accident. So you might have stomachache and suspected appendicitis. You go for a CT scan and actually whatever it was that was causing that is something else. And on the side, by the way, we accidentally, or not accidentally, we luckily found this kidney cancer in its early development. That's how most kidney cancers are found. We have this accidental early detection going on at a phenomenal rate, and it's very dependent upon how other diseases are treated. And so we have a treatment journey that's kind of independent of the disease itself. It's kind of like, let's hope we find it early, or it's going to become a much more serious disease. So how it might affect the treatment journey in the future is having something dedicated and set up. And what that means is it will look completely different. It's not an incremental process or incremental change. It's not going to be, oh, we'll have a slightly better drug. The introduction of AI will completely change. It'll make things possible that weren't possible previously. So I guess it's one thing, reducing waiting times and increasing treatment speed. It's another thing entirely to go through a national screening program where it wouldn't have otherwise been possible.
Yeah, absolutely. That could be a huge change, a huge impact on patient outcomes. I get it. So will it become standard of care? I'm guessing you hope it will. It sounds like it's a no-brainer to me. Can it be used outside of Cambridge? Are you already using it outside of Cambridge? I think I said the word Yorkshire in the introduction. So tell me a little bit about that.
So standard of care is something deeply protected behind many trusts and also by NICE. So that's the kind of health economic regulating body in the UK. And what they care about is, one, does your new proposed standard of care improve outcomes for patients, obviously, but two, does it do it at an acceptable cost? And unfortunately, we see many instances of drugs and other things in the news that would be good if we could provide them in the UK. They've perhaps shown effectiveness in the US or elsewhere in the world, but we can't afford them. They're too expensive for the UK. And so standard of care would look like, one, improving patient outcomes, and two, at an acceptable cost. If an AI almost inherently provides an acceptable cost, what we're doing is running something on a computer that otherwise would have to be looked at by radiologists or doctors. So what we're trying to show essentially that we can match that radiologist performance, and that's how we'll get it to standard of care.
Yeah, the ideal will always be that this will be applicable nationally, internationally, that it will work on all kinds of data. It doesn't matter what kind of CT scanner you have or MRI scanner. It doesn't matter what, how different your tissue looks. We should have models that are diverse enough that they capture the broad range of what you may see anywhere in the world. And that's really the ideal that we're working towards. How easy that is to deploy in the next 5 to 10 to 20 years will really depend on the regulations that come in on AI. And will really depend on kind of large scale collaborations between universities, between centres, between countries even. So yeah, that's definitely our goal. And in terms of the technological capacity of these models, we believe that it's possible, but there are a series of hurdles that we will need to overcome before we get to that stage.
Now, I know lots of patients have concerns about their data being used by AI. So how have you overcome challenges of training algorithms and using real-world data in a safe way for them?
Yes, this is a really big challenge for those of us who are working in AI, and we see it as really important as a research community that we remain open about how we use patient data. So we always de-identify and anonymize data before we use it to train our algorithms. It's stored securely in data storage systems. It's maintained by individuals who are really well trained in data access. And we always ensure that a patient has given consent before we store or use their data for any of the research that we do. Using real world data is really critical for us because it means that our models are much better. We use the word generalizable to mean that they can be applied to different cohorts than what they're tested on. And ultimately, we found that when patients understand that their data is being used securely and it's being used ethically, that many are supportive. And so we really want to maintain that kind of transparency, to have rigorous standards, to build that trust with patients, because yeah, it's really critical that we use real world data to develop these models.
Yeah, absolutely. So both of you have talked about your projects, and I think I'm right in saying that they're multidisciplinary projects. So you work with a whole range of people across different departments, perhaps in the university, and clinicians in the NHS. And so tell me a little bit about the challenges and opportunities of working in a multidisciplinary research group.
There's some important things to say first. So first, it's very important to get perspectives from all the different stakeholders. And as trite as it sounds, it's true. So what doctors care about is important. Equally, what engineers care about with maximizing AI accuracy, that's important. And getting access to, I don't know, medical physics in my domain, it's important to understand what affects, as Reb was saying, CT scanners acquire images in different ways across different hospitals. And so capturing the full heterogeneity of that, and making sure that patients are centered in our research is also important. So taking in all of these perspectives and disciplines definitely keeps you on the straight and narrow in terms of making something that's actually going to be useful. It's the only way, perhaps, to make sure you're going to make something useful for patients and for doctors. But it's also really important. There are perhaps more soft skills. There are more political points to learn. So, I mean, as with any organization, there's going to be politics and biases. And so doctors see themselves as guardians, for example. And that's a really important dynamic. And it's true. But for example, it means that when you communicate with, say, if you're designing an AI algorithm, you need data. It means that when in a multidisciplinary group, that you talk to doctors in a slightly different way, in a way that centers patient outcomes and centers safety and ensures that, as Reb said, we're going to de-identify data. We have these protocols in place to make sure your patients are safe and their data is safe. In other environments, when you want to absolutely maximize, and so your research is also maximizing AI accuracy, you're talking to some engineers, you need to convince them that this is worthwhile. And if it's worthwhile, then how do we push performance to, I don't know, for example, in screening setting to maximize your screening accuracy. And so that's an interesting technical problem. If you want to win engineers along, you might want to be pushing forward a technical solution. And so I guess the challenges are learning what all the different disciplines actually care about. The opportunity is that it's the only way to put something in front of a patient that's actually going to help them. But the challenges are all the different disciplines care about completely different things. And so, yeah, I guess that's what I'd say about that.
Yeah. I totally agree with everything that Bill just said. And the only thing I would add is that one of the big challenges that we find is actually, how do we communicate? How do we communicate our research really well? How do we make sure that it's not only, I have a biology background, Bill has an engineering background. And so we bring different things to the team, which is really useful, but we're also used to communicating in a slightly different way. I may be very interested in a particular kind of protein, where Bill has very deep understanding of how these machine learning or deep learning algorithms work. And so it's a challenge, but it's really good for us to be able to make sure that we can communicate our findings and communicate the architecture of the models that we're using in a really clear and concise way, so that not only do people in our research group understand, but also the clinicians, the patients, all of the staff that we're working with, so that we will understand what's going on, to keep it transparent, like we were saying earlier.
Yeah, and all of my listeners. So thank you very much. You've both been brilliant at that, actually. So I've only got a couple more questions to ask you. The first is, where do you see your research and your career taking you in the next 5 to 10 years? And if you want to answer both together, because it might be appropriate, where do you see integrated cancer medicine taking us into the next 5 to 10 years? So Rebecca, do you want to go first?
Yeah, sure. So I would love to continue working in this space, using AI to address these clinical questions, particularly these questions that have remained unsolved for so many decades. And it's really exciting to be working with AI now, because the speed at which these new techniques and models are being released means that this field is really hurtling forwards at an exciting pace. And it's really exciting to be involved in it. And I'd love to continue being there. I've also really enjoyed working at the interface between clinicians and industry and academia, and would love to continue doing that. We all have such a vested interest in seeing these questions answered. So yeah, I will continue to work towards kind of big collaborations to see our ideas through to fruition. And I'm keen to keep on working with those connections so that we can see AI models deployed in the clinic one day.
Brilliant. Fingers crossed. And Bill, last words to you.
Yeah, it's definitely going to be around how AI can provide help to us in our daily lives. And preferably, I'd like to stay within the space of working on kidney cancer. I mean, the one thing that we need to keep this going is access to more and more data. I mean, that's just going to be the theme of the next decades of research in AI. It's like, how do we use increasing amounts of data to improve these models further? And so I guess in the future, looking at things like how can a patient's clinical history can be used to inform even more accurate screening care, and essentially looking at what that means is pulling together data from different sources and integrating them. So how can integrated cancer data be used to improve patient care at the level of screening? For example, and this is a real problem that we faced in our screening, our model was extremely good at being sensitive to detecting cancers. So our AI model detected 100% of all kidney cancers within the Yorkshire Kidney Screening Trial. It did that with 93% specificity. What that means is for every 100 patients who didn't have anything wrong with their kidneys, 7% were highlighted by our model. So for every 100, 7 patients were highlighted, and the model said this patient should be double checked because I think there could be a cancer. Of those 7, roughly 4 had a cyst. What that means is over half of the mistakes made by our model were made on things that could have been ignored. And in fact, if you look at those patients' clinical history for all those, say, 4 of 7 patients' clinical history, their cyst was highlighted 2 or 3 years in the past. It was noted in a GP report, or it was noted on the bottom of a CT scan. Here's the cyst, it can be ignored. And so if you could pull together the knowledge from a patient's GP history or radiological history or from the hospital and say, hey, look, we know they have a cyst in this location. It's at the bottom of the left kidney. If you find anything else, let us know, but ignore that cyst. If you could do that, which technically that's a relatively simple task, actually, you could over double the accuracy of your model and makes your screening with AI even more effective. And so over the next, I'd say 5 to 10 years, we're going to be looking at how we can pull together as much of those different diverse data streams as possible to really maximize the screening accuracy.
Amazing. Well, I feel safe in the knowledge that you two are working on this stuff. Thank you so much for all of your work, and thank you ever so much for being on the podcast with me today. It's been a really interesting conversation. Thank you.
No, thanks for inviting us. It's been really fun.
Yeah, thank you, Anna.